The first pattern for drawing resonance structures that we're going to become familiar with is an allylic lone pair of electrons. So a lone pair of electrons that are allylic can participate in resonance. So we want to first be sure that we understand what the term allylic means. So if we have a pi bond, and that could be a carbon-carbon pi bond as shown here, or potentially something like a carbon-nitrogen or a carbon-oxygen pi bond. But the atoms of the pi bond itself are known as the vinylic positions. So these two carbons in this alkene are your vinylic carbons. The atom directly bound to those vinylic carbons are known as the allylic positions. And so we want to take a look at why this is special, this position that is immediately adjacent, directly bound to that vinylic position. So we've got two examples drawn here. We put in lone pairs. So this first oxygen with its lone pairs is directly bound to that vinylic carbon. So these are allylic lone pairs. The example shown below might look extremely similar, but the oxygen is separated from that vinylic position by an sp3 hybridized carbon. So these are not allylic. So these are not allylic lone pairs. All right, and if we try to delocalize these, that is to have them participate in resonance, we should be able to see what is the difference between these allylic lone pairs versus lone pairs that are not allylic. So resonance means that you can move your electrons, and we can always move for resonance only lone pairs or pi bonds. All right, so it may be helpful when you're first drawing these resonance structures to add in the hydrogens that are implied in our skeletal structure. So I'm going to go ahead and draw in these hydrogens. And the reason why we do this is because if we don't, it's easy to inadvertently put too many bonds on a carbon atom. So we're going to fill in these hydrogens. And we're going to draw a resonance structure. So we're saying that these lone pairs can participate in resonance. That means they're going to be shared by more than one atom. So they're going to be shared between this oxygen and this end carbon here. So we can indicate the movement of these electrons with curved arrows. So our curved arrow is going to show us that we can take one of those lone pairs and move it in here. So we're taking it from the oxygen and we're sharing it as a pi bond. Okay. If we stopped here, we will have put 5 bonds on this carbon atom. That's why we wanted to draw out these hydrogens so we could see it. So if we're going to push these electrons in, we need to have another set of electrons that we can push out. And that's the significance of this pi bond. So we can push that pair of electrons onto the carbon. So let's go ahead and draw that resonance form. Okay. So we have now a pi bond between the carbon and the oxygen. We had 3 lone pairs, but we moved 1 lone pair in. It's one of those bonds there. So now we have just 2 sets of 2 lone electron pairs on the oxygen. And then we don't have a pi bond between these 2 carbons anymore, and we've pushed that lone pair of electrons out onto the end carbon. Okay, and I'm going to go ahead and draw in those implied hydrogens again. So we had 1 here, 2 hydrogens on that end carbon, and we'll notice this end carbon now has a formal negative charge. So we are sharing that negative charge between the oxygen and the end carbon. So that's what these resonance structures are showing us. So this is shared between the oxygen and the carbon. Whenever you can share a formal charge, whether it's a negative charge or a positive charge, that helps to stabilize that charge. Okay, so that's why it's significant for us. And so if we look at this bottom example, we say this is not an allylic lone pair. You might think, well, can't we just draw the same arrows? So if we go ahead and do what we did to start here, and that's drawing these implied hydrogens, we'll see why we can't. So on this carbon, we see 2 bonds. That means we have 2 bonds to hydrogen. This carbon, we see 3 bonds, so we have 1 bond to hydrogen. and 2 hydrogens out here on the terminal carbon of that alkene. So we might think, well, can't we move these in? So let's go ahead and try. So we move it in. The problem then is we're going to have 5 bonds on this carbon, and now we don't have a pi bond that we can shift. If we're drawing resonance structures, we want to just be moving electrons around. We can't be breaking the molecule apart. And if we were to break this sigma bond, we'd actually be breaking apart that molecule. So we cannot draw this arrow because that would violate the octet on this carbon. So that would violate the octet rule. Okay, so we can do this delocalization as long as your lone pairs are allylic. So that means the atom with those lone pairs is directly attached to the atom that has that pi bond.